All right, Chapter 8 Energy Expenditure During Rest and Physical Activity. Objectives define basal metabolic rate and indicate factors that affect it. Explain the effect of body weight on energy costs of different forms of physical activity. Identify the factors that contribute to total daily energy expenditure. Outline the different classification systems for rating the strenuousness of physical activity. Describe two means to predict resting daily energy expenditure, or RDEE. Explain the concepts of exercise efficiency and exercise economy. List factors that affect the energy costs of walking and running. Identify the factors that contribute to the lower exercise economy of swimming compared to running. Okay, total daily energy expenditure is resting metabolic rate, thermogenic influence of consumed food, and energy expenditure during physical activity or in recovery. There's a great figure. There's a great figure on page 226. It talks about the percentages of total daily energy expenditure. Food is about 10%. So food intake, cold stress, thermogenic drugs. So the effects of feeding, thermic effect of physical activity. So that's in occupation, in home, sport, and recreation. So physical activity makes up about 15 to 30% of total daily energy expenditure. And the resting metabolic rate makes up about 60 to 75%, which deals with fat-free body mass, gender, thyroid hormones, protein turnover, sleeping metabolism, basal metabolism, and arousal metabolism. And one thing about the resting metabolic rate is 60 to 70. So physical activity does make up 15 to 30%. However, fat-free body mass makes up a portion of the 60 to 75%. So if you have more muscle mass, your resting metabolic rate is going to increase. Okay, so your energy is going to increase per day. So that's why muscle building activities through resistance training are so essential. Because physical activity burns calories right now, which is within that 15 to 30%, but you also have the resting fat-free body mass that goes up in that 60 to 75% of what is the expenditure, and that can be increased through resistance training. So if you have more of that, then you're going to burn more calories in your daily energy expenditure. Basal resting metabolic rate for each individual. Minimum energy requirement sustains body functions in the waking state. Body surface area, or BSA, frequently provides a common denominator for expressing basal metabolism. And basal metabolic rate averages 5 to 10% lower in females compared to that with males at all ages. And that has to do with females' larger percentage body fat and smaller muscle mass on average when compared with males. And that helps her lower metabolic rate per unit surface area be explained. So when women say, "Well, I have a lower metabolic rate than a man," that's why, I can't. I'm not burning as many calories. Well, it's true. Okay, it's true. Percentage body fat, more estrogen creates those types of things. So that's just it. I mean, it is a true statement from a physiological standpoint. It's not just a psychological or a statement made with no physiological basis. It has a physiological basis. Basal resting metabolic rate, and here it is right here. Females less than males, and so it's hormonally, things like that. And it decreases over age for both. Estimating resting daily energy expenditure. Metabolic rate per hour equals basal metabolic rate times surface area, or BSA. Predicting resting energy expenditure, women. Um, Resting daily energy expenditure. Uh, Basically, what you need to know about this is this looks at the hourly total provided. That provides important information to estimate the daily energy baseline requirement for caloric intake. Okay, it's a little bit different for men than it is women. Factors affecting total daily energy expenditure. Physical activity accounts for 15 to 30% of total daily energy expenditure. Dietary induced thermogenesis, or 10 to 35% of the ingested food energy. Climate, elevated core temp, additional energy required for sweat gland activity, altered circulatory dynamics, and pregnancy. Okay, those are the things that are factors that affect the total daily energy expenditure. One thing about the thermogenesis, dietary induced, this happens. This thermic effect of food happens about an hour after feeding, and it depends on food quantity, food types consumed. A pure protein, for example, if you eat pure protein, it produces a thermic effect often equaling 25% of the meal's total energy. Advertisements routinely tout the high thermic effects of protein consumption to promote high protein diet for weight loss. Advocates maintain fewer calories ultimately become available to the body compared to the lipid or carbohydrate rich meal of similar caloric value. Point has validity, okay, but other factors have to also be considered in prudent weight loss management. So they include harmful strain on kidney and liver function induced by excess protein, and cholesterol synthesizing effects of saturated fatty acids contained in higher protein foods from the animal kingdom. Because if you're eating more protein, some of the people doing that are doing it through a protein source, animal source, which is like animal meats, which is an issue in regards to cholesterol. Well-balanced meal plans require a blend of macronutrients with adequate vitamins and minerals. When combining physical activity with food restriction for weight loss, carbohydrate, not protein intake, provides energy for physical activity and concerns lean tissue invariably lost through food restricted dietary plans. So energy comes from carbs primarily. I mean, that's why the anaerobic, the primary source of energy is carbohydrates. So especially immediate energy. So those are things to think about. Climate-wise, resting metabolism of people living in tropical climates average 5 to 20% higher than counterparts in more temperate regions. So that plays a role too in daily energy expenditure. Okay. And that's based on elevated core temp, additional energy required for sweat gland activity, and altered circulatory dynamics. It's talking about the fact that it's hot out, so it's causing you to burn more calories, okay? Or burn more energy. More energy is expended, so it's in the form of calories. Okay, one of the things with pregnancy is that moderate physical activity presents no greater physiological stress to the mother than imposed by the additional weight gain and possibly encumbrance of fetal tissue. So they follow normal response patterns. Okay, this is on 5-level. This is the, I don't know, actually it's not that. So this is what factors affect total daily energy expenditure. Average rates of energy expenditure for men and women living in the United States. Okay, so this is the average of the energy expenditure that takes place. Okay, so, and then also talks about activities: sleeping, lying down 8 hours, sitting 6, standing 6, walking 2, recreational activity 2. Okay, and this talks about how much energy expenditure is what is the average male between this age, let's say 15 and 18, what do they expend energy wise. It's 3,000. Now, this is average. If you're a logger, let's say, you may be expending 4,500 calories per day, which we talked about in earlier chapters. Okay, that's you. So, this is average. Energy expenditure during physical activity. Body size plays an important contributing role in exercise energy requirements. Heavier people expend more energy. I mean, it makes more sense. It makes sense because obviously they have to. They're moving more mass. Okay, so they expend more energy to perform same activity than people who weigh less. Energy expenditure can therefore be predicted during weight-bearing exercise from body mass with almost as much accuracy as measuring oxygen uptake under controlled laboratory conditions. A MET is a metabolic equivalent. One MET represents an average adult's average seated resting oxygen uptake or energy expenditure. They're 3.5 milliliters of oxygen per kilogram per minute. Okay. That's okay. So 2 MET activity requires twice as much energy expended at rest, and so on. So here it talks about convenient way to rate exercise intensity from a resting baseline. One metabolic equivalent is an adult's average seated resting oxygen consumption or energy expenditure. Okay, 3.5 milliliters of oxygen per kilogram per minute, or 1 kilocal per kilogram per hour. Okay, this MET continue. Basically, this talks about the relationship between body mass and oxygen uptake measured during submaximal treadmill walking. Body size plays an important contributing role in energy requirements. So, heavier people expend more energy to perform the same activity than people weighing less. This is what body mass at the bottom, oxygen consumption on the side, y-axis. Efficiency of energy use. Mechanical efficiency is percentage of chemical energy expended that contributes to external work output, most affected by energy needed to overcome friction. Gross mechanical efficiency is total oxygen uptake during the exercise. Net mechanical efficiency is the resting energy expenditure subtracted from the total energy expenditure during exercise. Delta efficiency is ratio of difference between work output and 2 levels of work output to the difference. Ratio of difference between work output at 2 levels of work output to the difference in energy expenditure determined for the 2 levels of work output. Okay. All right, so if you want to look at these, these are on pages 234 and 235. Factors influencing exercise efficiency. So you have work rate. So as work rate increases, efficiency decreases. Okay. Which makes sense. Okay. Faster you do something, efficiency drops. Movement speed. Any deviation from the optimal movement speed decreases efficiency. Generally, the optimum movement speed increases as power output increases. Okay. Extrinsic factors. Improvements in equipment design have increased efficiency in many physical activities. For example, layer and softer running shoes with different insole cushioning properties permit running at a given speed with a lower energy expenditure. Muscle fiber composition. Work done with slow twitch muscle fibers is more efficient than the same work done with fast twitch fibers. Okay. Slow twitch fibers require less ATP per unit work than do fast switch fibers. So basically, if individuals who have the higher percentage of slow twitch muscle fibers exhibit increased mechanical advantage. Fitness level. More fit individuals perform a given task at a higher efficiency. Body composition. Fatter individuals perform a given task at a lower efficiency. And technique. Improved technique produces fewer extraneous body movements, resulting in lower energy expenditure, hence higher efficiency. Economy of movement. This is the quantity of energy to perform a particular task relative to performance quality. Can be assessed by measuring steady rate oxygen uptake during a specific exercise, a set power output or speed. At a submaximal speed of running, cycling, or swimming, an individual with greater movement economy consumes less oxygen, which makes sense. Okay, movement economy consumes less oxygen because they're more efficient in that movement. All else being equal, a training adjustment that improves economy of effort directly translates into improved exercise performance. Walking economy. Curvilinear relationship exists between energy expenditure versus walking at slow and fast speeds. So linear relationship exists between walking speeds of 3 to 5 kilometers per hour and oxygen uptake. At faster speeds, walking becomes less economical, so the relationship curves upward to indicate disproportionate increase in energy costs related to walking speed. So if you're walking really fast, speed walking, it starts to become less economically beneficial. So then there's too much energy costs with that movement. Okay, fast walking movement. So the crossover velocity is a place where at around 4 miles per hour, it's a juncture where running becomes more economical than walking. Okay, and that's just shown right here. Okay, you're walking faster. It's not economically advanced. You're using too much energy and swinging arms and things like that, walking fast, so then you start running at around 4 miles per hour. Okay, prediction of energy expenditure, kilocal per minute from speed of level walking versus and body mass. It talks about speed here. It talks about the body mass in pounds. Okay, and it's talking about how much energy is expended relative to the body mass. Okay, in the mile per hour. Okay, so you see a person at 80 mile per hour of 4 at 80 pounds, you're looking at 3.5 versus a 7. Okay, over there at 200. So it says how to use a chart. 120 pound person walks 3 miles per hour, expends 3.5 kilocal per minute. The person will expend 216 during 60-minute walk. Okay. So your body mass is on the top, speeds at the on the left side, and then you find that individual. You see how much kilocalories per minute. So you come down to 120 at 3 miles per hour, and you get 3.6. You see. So if you're at 120, and then you're saying, oh, what at 4 miles per hour, where am I at? Oh, I'm 4.7. Same individual. But as you see that the body mass, as it goes up, okay, the kilocalorie per minute goes up as well at the same speed. Walking surface and footwear effects. Walking surface, similar economies exist for level walking on a grass track or paved surface. Energy cost almost doubles walking in sand and is threefold when walking on soft snow. Obviously, because it takes more force to get through what those things are. So that makes sense. Footwear. More energy is needed to carry added weight on feet or ankles to carry similar weight attached on the torso. It's based on where the weight is positioned. And then ankle weights increase the energy cost of walking to values usually observed for running. Energy expenditure during running. Independent of fitness, it becomes more economical from an energy standpoint. Discontinue walking, begin jog at 4 miles per hour. We talked about that. Same total caloric cost results in when running a given distance at a steady rate oxygen uptake at fast or slow pace. Okay. And for horizontal running, the net energy cost per kilogram of body mass per kilometer traveled averages about 1 kilocal or 1 kilocal per gram per kilometer. Running speed can increase in 3 ways. All right, so we're on page 242. It increases by the number of steps per minute, stride frequency, number of increase in distance per steps, so stride length, and increase in stride length and stride frequency. One of the things on page 242 too talks about upper left corner exercise economy and muscle fiber type, that depending on what type of fibers you have in your muscles, that plays a big role in the economy of how you are able to move. Okay, distance running, muscle fiber type 1, if you have a high percentage of those predisposed, let's say, or trained, you're going to do better than someone with a type 2 muscle fiber type for distance running. Same thing with biking. It's talking about bicycling, and cyclists who exhibit the most economical cycle pattern possess higher percentage of slow twitch type 1 muscle fibers versus the fast switch type 2. So this is another thing that causes efficiency to be a factor, is the muscle fiber types in regards to what you're doing. Running speed, body mass. So talks about here net expenditure for net energy expenditure per hour for horizontal running in relation to velocity and body mass. So body mass, and then you look at the velocity, and then you look at, so you say that what you have an individual, if an individual is going at a quicker rate, and they are at the same rate, should I say, and they're displacing more body mass, their kilocalorie per mile is going to be higher. Air resistance, factors that influence how air resistance affect energy costs in running. Air density, okay, runner's projected surface area squared, a square of headwind velocity. And drafting, I mean, this is falling behind someone else that's running, or even bicycling. That's another, to counter the negative effects of air resistance and headwind on energy costs. So these are other factors, air resistance, that are pretty interesting in regards to how people try to, some of the variables that affect the cost of running. And bicycling too. I mean, you look at drafting is you see that on some of these Tour de France and things like that. People are riding behind other bicyclists to decrease the air resistance. Energy expenditure during swimming. Swimmers' energy expenditure differs from walking, running, and following ways. Energy to maintain buoyancy while generating horizontal movement at the same time during arms and legs, either combination or separately. Energy needed to overcome drag forces that impede the movement of an object through a water medium. These factors all contribute to a considerably lower economy swimming compared to running. Requires 4 times more energy to swim a given distance than to run the same distance, and these are based on the energy costs of drag, wave drag, skin friction drag, viscous pressure drag. And this is what we're talking about here, 3 components. You have the wave drag that's caused by the waves to build up in front of and form hollows behind the swimmer moving through the water. This component of drag only becomes a significant factor at fast speeds. Skin friction drag is produced when the water slides over the skin surface, Removal of body hair reduces drag to slightly decrease swimming energy cost and physiological demands during swimming. And then viscous pressure drag, which contributes substantially to counter propulsive efforts of the swimmer at slow velocities. It results from separation from the thin water sheet of water boundary layer adjacent to the swimmer. So the pressure differential created in front of and behind the swimmer represents viscous pressure drag.